Relations and of course on environmental science. To answer that question, we need only to look at the definition of environmental science, which is an interdisciplinary field of research that seeks to understand the natural world and our relationship to it. Our relationship to it. Those are the key words that tell us that environmental science is just as much about the natural world as it is about us, that is, humans. And for good reason. Since we emerged as our own species some 200,000 years ago, we have grown from a few thousand individuals to over 7 billion. And due to our sheer numbers, coupled with our impressive ingenuity, we as a species have become a force of nature. We can level mountains, make prairies out of wetlands, build dams to make lakes out of valleys and canyons, turn rainforests into vast stretches of farmland, all making what was once there naturally completely unrecognizable. Nowhere is this more apparent than from space. Here we see a picture taken from the International Space Station, featuring the Iberian Peninsula, which makes up the countries of Spain and Portugal. And just look at all those lights. These lights represent bustling metropolitan areas, which are filled with people and buildings, but also where we have changed nature to meet our own needs. We change the landscape to harvest resources and build our homes, and we call it progress. But all this progress often comes with unintended consequences: pollution, disease, resource scarcity, and overall environmental degradation. We like to talk about ourselves as if we are separate from nature, but we forget that we ourselves are animals, and that we depend on Earth to provide our basic essentials like food and shelter, and even to provide the resources that fuel our economies. A degraded environment leads to a degraded economy and ultimately a poor quality of life. As our numbers grow, our demands on Earth to provide also grow, and grow we have in recent years. Here you see a graph describing human populations from about 10,000 BCE, before Common Era, until modern day. Why start at 10,000 BCE? Well, that's the time when humans first experienced a population boom. Before that time, humans were primarily hunter-gatherers. But then we discovered something that would allow our numbers to steadily grow, and that discovery was agriculture. The cultivation of plants and animals provided us with excess food. This allowed humans to build large families as they switched from a nomadic lifestyle to an agricultural lifestyle. And thus, the agricultural revolution led to a small but steady population growth. World population growth was about 0.04% from that time up until about 1700 Common Era. And it was from 1700 until today that we have seen the most dramatic increase in our populations. This, of course, marks the Industrial Revolution, which provided us another big boost in energy as we began to effectively harness mechanical and electrical energy. The Industrial Revolution paved the way for improvements in sanitation, healthcare, vaccines, clean water, and nutrition, which has led to an increase in life expectancy and a decrease in infant mortality. All of this has allowed us to grow in a relatively short period of time from less than 1 billion to almost 8 billion humans calling this planet home. Will our numbers continue to grow at this rate? Can they? Can the planet sustain all of us? And when will we become too many for Earth to handle? If we want to continue to sustain our quality of life, it is imperative that we understand our population trends. What factors cause us to increase and decrease in population, and what we can do to influence the trends so that we can maintain a healthy home and planet. When we start to analyze and categorize the world population, we enter into the world of population ecology. Now, population ecology is a branch of biology that deals with the number of individuals of a particular species found in an area and how and why those numbers increase and decrease over time. For example, we could be studying the Ohio State University student population, who are all the same species, Homo sapiens, and who largely live in central Ohio. In general, population ecology is not unique to studying just humans. We could be talking about any species in any defined location, but here we will be applying population ecology techniques and terminology to understanding human populations around the world. And when applied to humans, we often call this branch of science demography. When describing the world population over the last several thousand years, we can take note of the two instances that allowed for dramatic growth, the first being the agricultural revolution around 10,000 BCE, and the second, the industrial revolution, much closer to modern day, about 1700 Common Era. So looking at this graph, how would you describe the growth? Well, this type of growth is pretty common among populations, and if you are familiar with mathematical functions, this might be an easy one for you. When we see a graph like this describing a population, we would say that the population is experiencing exponential or logarithmic growth. A key feature of exponential growth is that the growth depends on the size of the population, where a small population will yield small growth and a large population will yield large growth, so that the larger and larger and larger the base population becomes, the faster and faster and faster that entire population will grow. An example of another organism that experiences exponential growth are bacteria. Imagine that you are a scientist working in a laboratory and you want to grow a beaker of bacteria. So you prepare a rich medium filled with all the nutrients and luxuries that a bacteria will enjoy, and then you add one individual bacterium cell to the beaker. That's times 0. They're at the origin of this graph. But immediately, the bacteria starts to grow and multiply. Slowly at first, because the population itself is small. But as the base population grows, the rate at which the overall population grows also increases. We can calculate the growth with a simple equation, where the population of bacteria equals 2 to the nth power, n being the number of doubling times that have passed, and a doubling time being the amount of time required for a population to double in size. So for one individual to turn to 2, 2 to 4, 4 to 8, 8 to 16, etc. Using this equation, we could easily solve the following problem. What is the bacteria population after 24 hours? Our equation is the population of bacteria equals 2 to the n, and we're given our doubling time, which is 30 minutes. So we just have to find n. N after 24 hours times 2 doubling times per hour, since our bacteria doubles every 30 minutes, gives us an n of 48. So there will be 48 doubling times in our 24-hour period. We plug 48 into our equation, and that gives us a population of bacteria after 24 hours of growth of about 281.5 trillion bacteria cells. So you can see that in a relatively short period of time, our bacteria has grown from 1 to 281 trillion. That shows you the power of exponential growth, because in the first hour, we would only be 4, but by the 24th hour, we are doubling at immense rates. However, exponential growth cannot last forever, for any species and any population for that matter. At some point, the population starts to level out, and if nothing is done, the population will enter into decline. We see the theoretical growth that mathematically the population could continue to increase at an exponential rate, but it doesn't. Why do you think this happens? What is the limiting factor for population growth for our bacteria? If you thought, well, they must be running out of space, you would be falling into a common misconception. In fact, the bacteria have plenty of space, so physical space is not a limiting factor for population growth. The same is also true for the human population. Let's calculate how much space we would need if we were to place, let's say, 8 billion humans shoulder to shoulder. First, we need to know how much space one human occupies. Let's roughly estimate this by using the area of a circle, which is pi r squared. Let's assume that the average human is 0.61 meters in diameter, giving us the average area of a human where they would need to stand, of 0.292 meters squared times 8 billion humans gives us roughly 2,300 kilometers squared. So how big is that? If we think in terms of cities, New York City takes up roughly 1,500 kilometers squared, and Columbus, Ohio takes up about 550 kilometers squared. So we could fit all 8 billion humans, shoulder to shoulder, in less than 2 New York cities and in about 4 Columbus, Ohios. Really, relatively thinking for the whole of Earth, not that much space. Instead, the growth rates of our bacterial population slows and then eventually declines because of 2 main reasons. The first being that they simply run out of resources, which prevents them from reproducing. In human terms, running out of resources causes famine, if the resource is food, and in many times war, as countries compete for limited resources. The second reason is that the concentration of waste products starts to become toxic, causing death. Creating waste is a normal part of living, and bacteria are no different in this aspect. If you are familiar with fermentation, alcohol is a natural waste product of microbes that beer and wine makers use to create their libations. In human terms, waste products not only include our toilet waste, but also waste from industry and manufacturing, toxic chemicals like DDT and PCBs and plastics and trash. When we don't properly manage our waste, this leads to pollution and disease. The management of our resources and waste vary widely across the globe. Each country manages a little bit differently, and this largely is due to differences in culture. In order to get a better understanding, let's look at how humans are distributed across Earth. Here, you'll see a chart of the 10 most populous countries in the world. Right away, you may notice China and India up at the top of the list. China and India have led the world population for quite some time. Each holds about 18% of the world's total population. The United States, in contrast, is third on the list, but has about 5% of the total world population. Looking at China and the United States more closely, each have about the same land area, but China has a much higher population and therefore a greater population density. Population density is defined as the number of people divided by land area. This graph describes human population density by country, where the darker the green color, the more people there are per square kilometer, and the higher the densities. We see from this graph that population density is highly variable across the globe. The country of Bangladesh has the highest densities in the world at more than 1,200 people per square kilometer, while countries like Canada, Russia, and Australia have some of the lowest densities. But we should note that humans are not evenly distributed within their respective country either. Densities are many times higher in cities than in rural areas, and in general, the most densely populated areas in the world tend to be in coastal areas or close to major waterways. We rely on water for transportation and as an essential resource in our day-to-day lives. Water is such a driving force in where we live that it is estimated that about 90% of humans live on just 10% of Earth's surface area. This is largely due to our tendency to clump around essential resources like surface water. Population density is a useful metric, but it does not tell us much about resource use. When looking at resource use, we need to look at both where the resources are located in relationship to humans, as well as the rate at which those resources are being used. So it may be useful to look at biocapacity. Biocapacity being the ability for a given area to both provide resources as well as to assimilate waste. A population becomes unsustainable when their ecological footprint exceeds their area's biocapacity. We can also think about this in terms of carrying capacity, which is the maximum population size the area can support. This map describes biocapacity by country. The green countries are those whose populations' ecological footprints are less than their biocapacity, so they have not yet met their carrying capacity. The red countries, by contrast, are those who have exceeded their biocapacity and therefore have exceeded their carrying capacity. These are countries who have very large populations or have very high per capita use of resources, were initially resource poor, or who don't manage their waste effectively. These countries likely need to import a lot of goods to meet their citizens' needs. So we can see which countries are doing very well, living within their carrying capacity and below their ecological biocapacity, and which are not doing so well because they've exceeded their carrying capacity. But we live in a global economy, right? So maybe some countries are living beyond their means, but as long as other countries can share their resources and take some of that waste, it should all even out, right? Unfortunately, this isn't the case. As our population grows, so does our demand for natural resources, not only because there's just more of us, but also because our per capita use of resources is also growing. At around 1970, we began to use more resources than what our one single planet could provide to us sustainably. At our current rate of consumption, the human population is using almost 2 Earths worth of resources, 1.75 Earths. If we continue at this rate, we may very soon deplete all of our resources and suffer the very same fate given to our lab microbes. In a natural system, competition for limited resources and environmental degradation from waste and overuse help to limit population growth. Humans are not immune to these pressures. If our civilizations are to avoid these effective, yet very unpleasant, natural forces of population control, we need to take calculated action so that we curb the population growth of humans before these natural pressures take effect. And for that, we need to focus on the population growth rate. The growth rate being the percent increase of population size over time. This takes into account births, deaths, and the number of people moving into and out of a region, that is, immigration. Ultimately, the goal is to reach zero population growth. This occurs when the number of people born equals the number of people dying. This is also known as the replacement fertility rate. Reaching zero population growth takes 2 steps. The first is identifying why birth rates are high, and then taking steps to reduce them. So let's first take a look at why birth rates might be high. One explanation for high birth rates are known as pro-natalist pressures. These are policies or cultural beliefs that encourage families to have more children. Agrarian societies are well known for having high pro-natalist pressures, as the more children you have, the more hands you have to work the farm and complete household chores. But religious beliefs, the desire for an heir, prestige, and social status are also common social pressures for having more children. Some countries, like Russia, who have experienced a decline or shrinkage in their population, have encouraged families to have more children through government programs, incentivizing large families with financial or social benefits. Countries with high infant mortality also tend to have high birth rates, as families have more children to ensure they have children that survive to adulthood. We can also find relationships when looking at demographics. Factors such as access to health care, level of education, and economic conditions have all shown a general relationship to birth rates, and we'll look at each of these in more detail later. We often see large differences between more developed nations and less developed nations. Developed nations have a surprisingly high death rate, but this is due to an aging population. Higher infant mortality rates in developing nations reveal the differences in quality of life and access to quality health care. The high infant mortality reinforces high birth rates in less developed nations, which results in a high growth rate. So one strategy we may take to lower growth rates is to help less developed nations become more developed in hopes that it would improve their quality of life and help lower birth rates. We can see how this would play out by looking at the 5 stages of demographic transition. This theory suggests that as a country's economy changes from pre-industrial to post-industrial, that low birth and death rates will replace high birth and death rates. This happens because of improvements in quality of life that result in a change in the culture. So the goal to reduce birth rates would be to help move countries from stage 1 into stage 4 and 5. But we want to do this as quickly as possible, because during the transition in stages 2 and 3 is when the most population growth occurs. Populations grow during these stages because death rates fall before birth rates. Let's think for a moment about why this happens. Well, death rates are rather easy to decrease. Providing improved access to high-quality healthcare can vastly decrease death rates and infant mortality, as well as raise life expectancy. Increased incomes during these stages also increase quality of life, as families can afford necessities like food, shelter, and education, which also reduces stress and improves mental health and well-being. But birth rates, that's a cultural shift. In stage 1, families are having 5-10 children to ensure that some of their children survive to adulthood, because death rates and infant mortality are high here. So having large families with 5-10 children in stage 1 is the norm and the expectation. As infant mortality and death rates fall due to increased quality of life, the pronatal pressure lessens. But it may take 2, 3, or more generations for the expectation and norm to change from a large family to a small family structure. So generally, this is why birth rates often lag behind death rates being more closely tied to income and access, and birth rates being more closely tied to culture. When birth rates are higher than death rates, it results in a population that is very youthful. And it's these youthful and very young populations that have high growth rates, because the majority of the citizens are in or moving into their reproductive years. This results in population momentum. We can see this relationship by looking at these two maps side by side. The map on the left describes the population growth rate per country, where the darker the blue color, the higher the growth rate. The graph on the right describes the median age per country, where the lighter the color, the more youthful the population. We can see that in general, countries with low median ages or youthful populations also tend to have high growth rates. Look at Africa, for example. But we can also see the opposite. Japan and several European countries have some of the highest median ages and are actually experiencing negative growth rates. Age structure diagrams allow us to analyze a population in more detail. Demographers use age structure diagrams to predict the population's future growth potential. Here is the age structure diagram of West Africa. The bars represent the percent of the population within each age group. The age groups are listed along the y-axis, starting at 0 to 4 years and ending at 100 years old. The x-axis describes the percentage. You'll see the x-axis starts at 10%, decreases to 0%, and then increases again to 10%. This is because each age group is further broken down by gender, with males on the left and females on the right. So we can see the composition of the population in great detail. For example, 5.2% of the population are females between the ages of 15 and 19, whereas 2.7% are males between the ages of 35 and 39. But maybe more telling is the overall shape of the age structure diagram. A quick glance of the shape tells us a lot about the future growth potential of the population. See how different these three diagrams look from each other. West Africa is a dramatic pyramid shape with the majority of its population at the base. This makes for a very young population. Its median age is very young, so the majority of the population is in or is moving into their reproductive years. This population, more than the other two diagrams shown, has a very high growth potential and high population momentum, meaning that if the growth rates were to suddenly drop to 0%, there would still be a lot of population growth simply because a large portion of the population is moving into their reproductive years. The diagram on the far right, by comparison, is the age structure of Western Europe. It shows the largest portion of the population up at the top, so the population is aging. The majority are at the end of or are leaving their reproductive years. So the population has a low growth potential and low momentum. Growth rates are declining. The diagram in the middle describes the population in Western Asia, which is somewhere in between of our two extremes. Notice how the shape is pyramid in nature, but not nearly as dramatic as West Africa's. Less developed countries generally have high growth rates and will more resemble the diagram on the left, whereas highly developed countries generally have low growth rates and will resemble the diagram on the right. And the higher the growth rate, the more quickly a population will double in size. We can use the rule of 70 to calculate the amount of time in years it would take for a population to double. This simply has us dividing 70 by the annual growth rate. We can see from the graph that the annual growth rate of the world has been steadily declining since it peaks at around 1962. The United Nations projects that the growth rate will continue to decline over the next century. Should we expect the population to double by then? Let's use the rule of 70 to find out. Our problem states, at our current rate of growth, in what year should we expect the world population to double in size? Our equation is the rule of 70, where the population doubling time equals 70 divided by the annual growth rate. The current annual growth rate is 1.08%. So 70 divided by 1.08 equals 64.8 years. Add this to our current year, and at our current rate of growth, the human population will double to 15.4 billion people by the year 2085. So given current trends, we should expect our population to double again before the end of the century. Because note, while world growth rates are declining, the overall number is still greater than 0. So the population is still growing. The population will continue to grow until growth rates are at 0 or is negative. We can see how the world population is projected to grow by looking at the graph. The teal color describes the population number, and the purple line describes the growth rates. The growth rate is declining, so our overall growth is slowing, but it's still growing because the growth rate is above 0. We can see this as well if we look at the world's age structure diagram. It is transitional in state, but because it is a pyramid, we should expect there to be future growth. So, are these trends good enough, or should we be doing something more to usher us towards 0 growth rates? Just as there are many explanations as to why birth rates might be high, there are many actions we can take to reduce them. Let's take a closer look at the strategies that have been used. To illustrate the first strategy, let's look at China as a case study. China experienced severe hardship in the middle of the last century. Between 1959 and 1961, China experienced an extreme famine that claimed tens of millions of lives. Then, in the 1970s, there was a shortage of consumer goods like soap, eggs, and sugar. The Chinese government blamed both these events on overpopulation, and so in 1979 they initiated the one-child policy. The hope of the policy was to drastically decrease fertility rates to prevent extreme events like these from occurring again. This is an example of a top-down approach to population planning, where a decree about fertility and family size is decided upon and enforced by the government. The Chinese government claims that the policy is responsible for preventing some 400 million Chinese births. And while largely supported by its people, the policy is highly controversial outside of China. This is because the Chinese government resorted to controversial methods to enforce the policy. Experts and witnesses tell accounts of forced sterilization, forced abortion, sometimes well into the 3rd trimester of pregnancy, infanticide, and restriction of health care for unsanctioned births and for the children that resulted from them. The extent of these practices are largely unknown, as records either do not exist or are not shared outside of China. And, sadly, the majority of demographers today feel that birth rates in China would have fallen regardless of the policy. This is because during this time, like many other countries around the world, China was experiencing a demographic shift. Their culture was moving away from a rural agrarian culture, where pronatalist pressures are high, to a major urban and industrial culture, where small families are the norm. Fertility rates in China had already halved before the introduction of the policy in 1979, and while birth rates continue to fall, so did birth rates in similar countries like Taiwan, who did not experience a policy like this. So it begs the question, how truly effective is this top-down approach? Many would argue that this approach is highly ineffective, so let's look at some alternatives. Bottom-up approaches are more the norm across the globe. They focus on social justice issues associated with overpopulation. It is the philosophy that addressing factors that decrease the death rate will also decrease overall population growth rates. But remember that birth rates are largely influenced by culture, so programs that address the needs of a population and that work within the cultural and religious traditions are the most successful at reducing pronatal pressures. This means that what works in the United States won't necessarily work in Afghanistan, what works in Indonesia won't necessarily work in Guatemala, and so on. Bottom-up approaches are highly tailored to the target population, but there are also general trends that seem to work in most countries. One such trend is the relationship between fertility rates and child mortality. We've spoken briefly about this relationship, but here we see it visualized. The x-axis describes child mortality, which measures the share of children that die before their 5th birthday. On the y-axis, we have the average fertility rate per woman. And we see a general trend where the lower the child mortality, the less children women tend to have. When child mortality is high, so is the fertility rate. Uganda, for instance, has a child mortality rate of about 9%, and their average fertility rate is almost 6 children per woman. The world average has a child mortality rate around 5% and an average fertility rate of 2.5. Looking at this trend, it is expected that if we put our efforts into reducing child mortality rates, that we can help to bring down average fertility rates as well. We see another general trend when we compare fertility rates and a woman's educational attainment. Shown on the x-axis is the average number of years of schooling of women in the reproductive age between 15 and 49 years. On the y-axis, we find the total fertility rate, which is the number of live births per woman. Looking at the graph, we see a general trend where educational attainment and fertility rates are negatively correlated. In other words, the more years of schooling a woman has, the less children they tend to have. The less years of schooling, the more children they have. Looking at this trend, we expect that if we put our efforts into providing women access to education, that we can help to bring down average fertility rates as well. Here, we see actual fertility rates compared to wanted fertility. The wanted fertility is an estimate based on survey data of what the total fertility rate would be if all the unwanted births were avoided. And we see, as we should expect, that actual fertility and wanted fertility are positively correlated, so that the more children a family wants, the more children they have, and vice versa. Here you can see that actual fertility rates are slightly higher than wanted fertility. Most countries hover just above the line, which marks if wanted fertility and actual fertility were the same. Uganda, for example, has a wanted fertility rate between 4 and 5, and an actual fertility rate between 5 and 6. Pakistan has a wanted fertility of 3, but an actual fertility above 3, almost to 4. Looking at this trend, it is expected that if we help families prevent unwanted births, that we can help reduce the average fertility rate as well. And one way to prevent unwanted births is through family planning programs and contraceptives. The bottom graph describes fertility rates and contraceptive prevalence, showing a negative correlation between the two, so that the more prevalent contraceptives are, the less children women have, and the lower the fertility rates. This should be pretty obvious, but it also helps to support how effective the use of contraceptives are at preventing pregnancy, especially unwanted pregnancy. The map describes the unmet needs for contraceptives among married women of reproductive age. Unmet need for contraceptives is measuring the share of fertile married women of reproductive age who do not want to become pregnant but are not using contraceptives. The darker the red color, the more of a need there is. And we see that especially in Africa, where we know birth rates are high, that there is an unmet need. This may be an issue of simple access, but it may also be an issue of culture. For countries where desired fertility rates are high, such as Niger, providing contraceptives may have little impact on total fertility rates. Lastly, let's look at how income impacts fertility rates. Here we see a graph comparing the two, and we see again that income levels and fertility rates are negatively correlated, so that the more income a family has, the less children they tend to have. Looking at this trend, it is expected that if we help low-income countries develop economically, that this may spur a demographic transition similar to that experienced by many industrialized nations, and that this may help reduce the average fertility rates. These last few trends are so strong and universal between countries that many demographers believe that addressing social justice issues, especially improving the health and well-being of women and children, are the key to reducing total fertility rates around the world. But we live in a very complex world, and simply reducing fertility rates may not be good enough. This is because as nations industrialize and incomes increase, the demand for resources also increases. Industrialized nations have a much, much higher per capita use of resources than do less developed nations. We buy more goods of all kinds, and the price that we pay for those goods do not reflect their true costs. The environmental and social costs are often left out of the retail price. This is a cultural issue, and it's not going to be one that's easy to fix, but we can start by buying less, buying only from socially and environmentally responsible companies, purchasing quality-made items with long functional lives, and buying used or secondhand as often as possible. Diets have also been shown to change as nations become more developed. Higher incomes and urbanization are associated with an increased demand for meat and animal proteins. While the global meat industry does provide food and livelihoods for billions of people, it also has very significant environmental and health impacts. Meat is many times more intensive to produce than fruits and vegetables and grains. And this is another very strong cultural issue, but we can begin to make an impact by reducing the amount of meat and animal products that we consume. Ideally, this means a diet that's vegan or vegetarian, but just cutting meat out of one meal or even just one day a week can significantly reduce your ecological footprint. Human population projections range from 6 billion to 16 billion by 2100. What do you think the human population carrying capacity is? How many humans can Earth support? Well, if we want to all live like Americans, who have an exceptionally high ecological footprint, the Earth will be able to support a much smaller population than, say, if we all lived like Africans, who currently have a much smaller ecological footprint. We should also factor in values and worldviews. Do we expect all of Earth's resources to support humans only? Or is there value in reserving resources and land for those other organisms who we share Earth with? Lions and tigers and bears, oh my, the more land and resources we take to support our own populations, the less we leave for wildlife. We are in the midst of a major mass extinction, largely due to humans destroying wildlife habitat. If living in a world without our large, iconic animal species is acceptable, then we may have a larger carrying capacity. Ultimately, the question of how many people the planet can support may not be the right one. Trying to pinpoint whether Earth's carrying capacity is 7 billion or 9 billion is meaningless unless we identify what an acceptable quality of life is.